All right, so today we're going to be looking at something that sounds a little like magic. This
Yeah.
idea of getting something from nothing.
Yeah, it's one of those.
Usually you hear that and you think, oh, philosophy or, some kind of magic trick.
Right.
But it turns out it's a question at the cutting edge of physics.
Absolutely.
So we are deep diving into some excerpts from Terrifying Quantum Theory for Scientists.
Oh, yeah.
Don't let the title scare ya. It's actually pretty fascinating. Our mission today is to unpack how modern physics really flips our understanding of reality on its head,
Right.
especially this whole idea of nothingness.
It is quite a shift.
Yeah.
For centuries, we pictured the universe as this collection of objects, but it turns out it's more accurate to think in terms of fields.
Okay, so right off the bat, we need to get this fields concept clear.
Sure.
It's not exactly something we encounter in daily life.
Right.
What's a good way to wrap our heads around this?
Well, think of a swimming pool.
Okay.
The water itself is like the field, and the waves or splashes are disturbances in that field.
Gotcha.
Those disturbances are what we perceive as particles.
So the field is like this underlying stuff that's everywhere. And
Yeah.
the things we see as solid objects are just temporary ripples in that stuff.
Exactly.
Whoa.
And one of the most mind-bending discoveries in physics is that even if you remove all matter,
Okay.
all the stuff we can see and touch,
Right.
these fields still exist.
Mm.
They're fundamental to the very fabric of the universe.
So even the seemingly empty space between stars and planets,
Yes.
it's not truly empty.
Nope, not at all.
Really?
What we think of as vacuum is actually buzzing with activity,
Okay.
full of these quantum fields constantly interacting.
Hmm.
It's kind of like a simmering pot of energy waiting to bubble over.
This is where it starts getting a little bit spooky for me.
Yeah.
If empty space is actually this hidden energy field,
Yeah.
what kind of evidence do we have that this is real and
Yeah.
not just some theoretical idea?
Yeah. One of the most convincing pieces of evidence is something called the Casimir effect.
Okay.
It's a measurable force that proves emptiness is actually full of fluctuating electromagnetic fields and these things called virtual particles.
Virtual particles.
Uh-huh.
Okay, now you're making me think of science fiction movies.
It does sound a bit like that, right?
Yeah.
But it's a real phenomenon.
Okay.
Imagine two plates placed incredibly close together
Okay.
in a vacuum.
Okay.
Logically, you'd expect them to just sit there,
Right.
maybe experiencing a tiny bit of gravity.
Right.
But that's not what happens.
Wait, so something actually happens to these plates in a vacuum?
Uh-huh.
What, are they moving or something?
They actually get pulled together with a force much stronger than gravity can explain.
What?
It's almost as if the space itself is pushing them together.
Okay. That's seriously freaky.
Yeah.
How can the space around them be doing that?
It all comes down to those virtual particles we mentioned.
Right.
They're constantly popping into and out of existence all around us, like tiny fleeting disturbances in the quantum fields.
Hmm.
But between those two plates,
Yeah.
the space is so small
Yeah.
that some of these virtual particles can't exist there.
So it's like there's more pressure from these particles on the outside of the plates than on the inside.
Exactly.
Yeah.
More virtual particles are pushing on the outside, and that difference in pressure forces the plates together.
Hmm.
It's this invisible hand squeezing them, and it's measurable.
That's a pretty solid piece of evidence for something that sounds so unbelievable.
Right.
But I have to ask, are these virtual particles the same as the regular particles that make up?
That's a great question.
Well, us and everything we see.
That's where it gets even weirder.
Okay.
They're not real in the way we usually think about matter,
Okay.
but they do have these real measurable effects.
Hmm.
Imagine them as these fleeting glimpses of particles
Okay.
borrowing energy from the vacuum,
Okay.
popping into existence for a tiny fraction of a second, then vanishing again.
So they're like boosts of particles.
Yeah, kind of like that.
That's mind-boggling.
Yeah,
But hold on, I thought we were talking about getting something from nothing.
right.
Are you telling me these ghost particles can become real?
That's where we enter the territory of something called the Schwinger effect, and things get even more interesting.
Okay, I'm all ears.
All right.
What is this Schwinger effect?
Okay.
And how do we go from ghost particles to actual matter?
All right. So the Schwinger effect is, it's a theoretical prediction made by Julian Schwinger.
Okay,
He was a giant in the world of quantum physics.
gotcha.
And he proposed that if you have a strong enough electric field,
Yeah, okay.
you can actually rip particle-antiparticle pairs out of the vacuum,
Hold on.
making them real.
Back up a second.
Yeah?
Are we talking about creating something out of nothing?
Well,
Isn't that breaking some fundamental law of physics?
it's not exactly creating something from absolutely nothing.
Okay.
the energy to create these particles comes from the electric field itself.
So you're basically transforming energy into matter.
Think of it more like converting energy into matter.
Right.
Which, when you really think about it, is still pretty mind-blowing.
Yeah, that's like Einstein's famous equation, E equals mc squared in action.
Yeah.
So we're talking about transforming pure energy into tangible matter.
Right.
Has anyone ever actually observed this Schwinger effect?
Yeah, that's a good question.
I mean, it sounds pretty theoretical.
For a long time, it was purely theoretical.
Right.
We just couldn't create electric fields strong enough to test it in a lab.
Yeah.
But recent breakthroughs, using a wonder material called graphene, have brought the Schwinger effect from the realm of theory into reality.
Okay, wait, isn't that the stuff they use in like those super strong tennis rackets?
It is.
What makes it so special for studying this something from nothing idea?
Well, graphene is incredibly strong and versatile.
Yeah.
But for physicists, it's like a playground for exploring quantum phenomena. It's essentially a single layer of carbon atoms arranged in a honeycomb pattern. And it has some very unique properties.
Okay, like what?
For one thing, it can withstand incredibly strong electric fields without breaking down.
Wow.
Because it's so thin,
Yeah.
essentially two-dimensional,
Okay.
it allows scientists to manipulate electrons in ways that are impossible with bulkier materials.
So how did they actually use graphene to observe the Schwinger effect?
Researchers at the University of Manchester created a superlattice structure using multiple layers of graphene arranged in a specific pattern.
Okay.
Then they applied a strong electric field
Okay.
and watched what happened.
And did they actually manage to pull particles out of thin air?
They observed electron-hole pairs popping into existence seemingly out of nowhere.
Wow.
It's not exactly the creation of electrons and positrons as predicted by Schwinger,
Okay.
their antimatter counterparts,
Right.
but it's a condensed matter analog of the same process.
So they basically recreated the conditions of the early universe, but in a tiny piece of graphene?
In a way, yes. And it's a stunning confirmation that even in seemingly empty space,
Yeah.
the potential for something to emerge is always there.
Okay, so we've got this buzzing void full of quantum fields and virtual particles that can become real under the right conditions.
Yeah,
It's a lot to take in,
it is.
but I can't help but think about the vastness of space, the emptiness that astronauts experience.
Right.
Doesn't that contradict all this?
That's a great point, and it brings us to a very human perspective
Okay.
on this whole idea of nothingness.
Okay.
Think about those images we've all seen of astronauts floating in space,
All right.
surrounded by that inky blackness.
Yeah.
It looks empty, right?
Yeah, it's the classic image of the void.
Yeah.
But you're saying even that emptiness isn't what it seems.
Exactly. That empty space is actually teeming with the very quantum fields.
Wow.
And virtual particles we've been discussing,
Mm-hmm.
our human perception of emptiness just doesn't line up with the reality of the universe.
So this nothingness we imagine when we think about outer space is really just an illusion, a trick our brains play on us because we can't perceive these quantum fields.
It is.
Wow.
It's a humbling reminder that our senses can only take us so far in understanding the universe.
Right.
There's a whole hidden world out there operating by rules that defy our everyday experience.
So if true nothingness is basically impossible,
Yeah.
what does that tell us about the universe we live in? What are the implications of this always-on buzzing reality?
It points to a universe that's inherently dynamic, constantly in flux, at the most fundamental level. Even the vacuum state, the lowest energy state, isn't static.
Okay.
It's full of potential, with virtual particles popping in and out of existence
right.
and fields interacting in complex ways.
So the universe is never truly off. It's always doing something, even in the seemingly emptiest corners of space.
Precisely.
Wow.
And this has some pretty wild implications for our understanding of how the universe began
Okay.
and how it might end.
Okay, now you've really got my attention. Tell me more about what this means for the big picture. Okay, so we've established that the universe is never truly off.
Right.
It's always simmering with this quantum activity, even in the places that seem empty to us. It's a pretty radical shift in perspective.
It is.
But I have to wonder, what does this actually mean for us here on Earth?
Yeah.
Does knowing that nothing is actually something change anything practical?
That's a great question, and it gets to the heart of why we do science in the first place.
Right.
While some of these concepts might seem purely theoretical,
Yeah.
they have the potential to completely revolutionize our technology
Okay.
and deepen our understanding of the universe.
Okay, I'm intrigued. Give me an example. How could something like the Casimir effect,
Yeah.
those plates being pushed together by virtual particles, actually be useful in the real world?
Well, on the nanoscale, the Casimir effect becomes a significant force as we develop ever smaller devices,
Okay.
tiny sensors,
Yeah.
microchips,
Yeah.
even nanomachines. We need to understand how these quantum forces will affect their function.
Okay.
Imagine building a microscopic robot
Okay.
that can navigate the human bloodstream.
Right.
You can't ignore the Casimir effect at that scale. It could make your robot stick together or malfunction.
So it's like a whole new set of engineering challenges and
Right.
possibilities, all because of this force that comes from empty space.
Exactly. It's a great example of how something that seems abstract and theoretical
Yeah.
can have very real and practical implications as our technology advances.
That makes a lot of sense. What about the Schwinger effect?
Sure.
This idea of creating matter from energy is incredibly cool,
Yeah,
but it also sounds like something straight out of science fiction.
it does.
Could we ever get to a point where we're like materializing objects out of thin air?
Well, let's not get too carried away.
Okay.
The energy requirements to create even a tiny amount of matter using the Schwinger effect
Right.
are astronomical. We're not going to be 3D printing cars out of pure energy anytime soon.
Okay, so maybe not flying cars just yet.
Right.
But are there any potential applications for this kind of technology, even on a smaller scale?
Absolutely. One area of active research is in particle physics.
Okay.
Understanding how particles and antiparticles are created and destroyed
Uh-huh.
could lead to new ways of generating energy or even probing the fundamental nature of matter itself.
So the nothing of the quantum vacuum
Yeah.
could hold the key to unlocking some of the biggest mysteries of the universe.
It very well could, and that's what makes this field so exciting.
Yeah.
We're literally just scratching the surface of what we know about the quantum world,
Right.
and every new discovery opens up a whole new realm of possibilities.
It's mind-blowing to think that something we perceive as nothing could
Yeah.
be so fundamental to, well, everything.
Right.
So to wrap things up for our listener today,
Okay.
what's the big takeaway from all this?
All right.
What should they be thinking about as they go about their day, encountering the apparent nothingness of their daily lives?
I think the key takeaway is this: emptiness is an illusion. What we perceive as void is actually a sea of potential, of quantum fields and virtual particles constantly interacting and shaping the fabric of reality.
Oh.
Even the most mind-blowing events like the creation of the universe
Yeah.
might be rooted in this fundamental truth.
So as we go about our lives, we should remember that even the seemingly empty spaces around us
Yes.
are teeming with possibility and potential, just waiting to be understood
Right.
and maybe even harnessed.
Absolutely.
It's a pretty awe-inspiring way to look at the world.
It is, and it's a great reminder that there's always more to discover, more to learn. Our journey of understanding the universe is far from over.
That's a perfect note to end on. So to our listener, keep those minds open and keep asking questions.
Yeah.
The universe is a much stranger and more wonderful place than we could have ever imagined.
And who knows, maybe someday we'll even learn to harness the power of nothing to create something truly extraordinary.
That's it for our deep dive today.
All right.
Thanks for joining us on this journey into the mind-bending world of quantum physics.
It's been fun.
We'll be back next time with another fascinating exploration of the world around us.
Sounds good.
Until then, stay curious.